we're going to do a demonstration of how you can compute simulated distillation column. You just have to open a new case. The first thing is the components. You have to select components. We're going to select a mixture, a binary mixture composed of benzene and toluene. So we click on the Add tab and we add benzene and toluene. We can close now this window, and we have to select the fluid package tab. We add the thermodynamic model that we are going to use for our calculation, which is the Antoine equation here, because we're dealing with the ideal binary mixture. So now we have two components and the fluid package, the Antoine equation. We can now enter the simulation environment, and we have the PFD here, the process flow diagram. We add a stream, which will be our feed stream. We can call it feed. This feed stream will be saturated liquid, so I choose a vapor fraction equal to 0. I don't have to fix the temperature, but I'll need to fix the pressure. 101.325, 1 atmosphere. 101.325 kilopascal. The molar flow rate will be equal to 10 and kilomole per hour, and I will have to click on the molar flow rate to fix the composition of the stream, the feed stream, and I'm going to choose a Nicky molar stream with moles fraction equal 0.5. Total mole fraction will be 1. I click OK. Now this stream is defined, and you see HYSYS has computed automatically the boiling temperature of this stream, which is 91.18 degrees Celsius. Now I have to choose my distillation column. I can click and drag on the distillation column and open the distillation column. The feed stream will be on stage 5. The distillation column will have 10 stages. I choose total condenser. I name the distillate stream D as distillate, the bottom stream B as bottom. The reboiler energy will be called R, and the condenser energy stream will be called C. Now it allows me to go to next, so I choose next. I'm done with this page. This I'm not gonna modify it. I'm gonna use the HYSYS, regular HYSYS reboiler. I'm gonna move on to the pressure drop. I'm gonna choose uniform pressure throughout the column, so no pressure drop. So the pressure will be 101 kilopascal. Now I can choose next. This is optional, so I'm not going to do anything about it. I choose next, and I'm going to choose done. Now a window open, and I'm going to choose monitor here. Okay, here is where I specify the additional specification that I have to do to have 0 degree of freedom. So let's get rid of this for the time being. So I have a degree of freedom of 2. Now let's eliminate this. Let's eliminate this. Let's eliminate this. I'm going to choose a reflux ratio equal to 2. And I'm going to make it active. So now the degree of freedom is 1. So I have to add another specification. The specification will be a component, column component fraction. So I'm going to choose the condenser, and I'm going to choose benzene, and I'm going to choose a liquid mole fraction of 0.95. Now the degree of freedom is 0, and I can run my column I choose run, and it says converged. As you see, everything now has converged. Everything is in dark blue or in black, so everything is fine. I can see the composition profile and the temperature profile in the column by choosing plots. Plots, temperature profile, view graph. Here is the temperature profile. The temperature in the bottom of the column is around 110, which is the boiling temperature of toluene, and in the top of the column is 80 degrees Celsius, which is the boiling temperature of benzene. I can choose to see the column composition profile. Here is I have the benzene and toluene liquid mole fractions throughout the column, and I see that I have very good separation. Indeed, in the top of the column I have almost one mole fraction, one as a mole fraction, 100% mole fraction of benzene. In the bottom I have only toluene almost. Okay, this is a simple binary mixture, ideal binary mixture that doesn't show anisotrope, so we get very nice results. خلاص.